In this video, we're just going to look at a quick introduction to a very interesting and important formula called Euler's formula, named for the Swiss mathematician Leonhard Euler, one of the great mathematicians of all time, who lived shortly after the time of Newton and did a lot of important work in calculus, analysis, differential equations, looked at a lot of applications to different areas of physics and a lot of other fields and a lot of other important work in mathematics. So for starters, we think about general complex numbers. Z is x plus iy, and we can picture that geometrically as a vector in the xy plane, where we're thinking about x, the real part, being the first component of our vector, and y, the imaginary part, the second component of our vector. We can picture any complex number this way geometrically. Then we use the usual expressions for relating the x and y Cartesian coordinates to the trig functions and just substitute those in here. That gives us our complex number. Essentially any complex number in polar form is r cosine theta plus ir sine theta, and then we have a common factor of r which we can pull out, which is what's happening here. So that's basically any complex number in polar form, and that has applications in pre-calculus and physics and engineering, electric circuits, a lot of different applications of that formula. We're going to go ahead next in step 2 of this derivation and focus on the angular part and just ignore the r part for now. So we'll define f of theta to be the angular part of the previous expression, just cosine theta plus I sine theta. And when we calculate the derivative of that, something interesting happens. Just different the derivative of cosine theta, the real part, is negative sine, and the derivative of I sine is just I cosine. So that gives us this expression for the derivative of f of theta. Now it's fairly easy to see if you just take your expression for f of theta and multiply it by I, it's fairly easy to see that you get the expression that we just got for the derivative, since I squared is -1. So f prime of theta is the same thing as I times f of theta. And here we need to recall this fact, which we talked about quite a bit in the previous chapter. Anytime you have a situation where you have a function whose derivative is a multiple of the function itself, which is what this differential equation is saying, then the solution of that differential equation must always have that exponential form, an exponential times the initial value. And that's exactly what's going on here. We have the derivative of f of theta is a constant multiple, in this case I, times our function. So using that little orange box on the right, we know that f of theta must be equal to f0 times e to the I theta. And looking at our formula for f of theta that we started off with here, and plugging in 0 for theta, we see that f of 0 would be cosine 0 plus I sine 0, which is 1 plus 0, or 1. So plugging in that initial value, we get f of theta is e to the I theta. So the function that we started off with, the angular part of our expression for any complex number. We started off with cosine theta plus I sine theta, and that short derivation shows that that expression is always equal to e to the I theta. This is a very important and useful formula that has a lot of connections to a lot of different subjects. Any student who is continuing on in engineering or physics or applied mathematics is probably going to see this formula again in connection with Fourier series, Fourier transforms, and electric circuits, and a lot of other things. We'll probably make some use of that formula as well later on in this course in some of our work on Laplace transforms. Very important and useful formula, definitely worth remembering.